This is the 10th lecture on continuity. Today, we will see one of the most important property of a continuous function defined over a closed and bounded interval. It says that if a continuous function is positive at a point and negative at another point, then the function must be zero at some point in between. So, in technical words, let AB be a closed and bounded interval and f from AB to R be a continuous function. If FA into FB is negative, that means they are of opposite signs. So one of them is positive, other is negative. Then there is a point in between A and B where the functional value at that point is zero. This is named as Bolzano's theorem. The proof contains one of the most important construction in the analysis. Let's see. Without loss of generality, assume that the function is negative at the left end point and is positive at the right end point. Call A equal to A1 and B equal to B1. Why do we want to do that? The reason will be evident in a moment. We look at the midpoint of this domain, of this interval, A1 to B1. So C1 is the point A1 plus B1 over 2. Now, three cases may happen. It may so happen that the functional value at C1 is 0. In that case, this C1 is our xi, our desired point xi, and we are done. Otherwise, the value at C1 can be positive or negative. Now, depending on that, if the functional value at C1 is positive, then we choose the subinterval A1 to C1 and discard the rest of the portion. Otherwise, as is the case in this example, if it is negative, then choose the subinterval C1 to B1 and call it A to B2. Okay, and in that case, discard the left side of the subinterval. A1 to C1 you discard. You keep the subinterval C1 to B1. Now, why are we doing this? I mean, what is the crux of this construction? The crux is to keep the desired point in the middle of the domain. We are guaranteed that at the left extremity, in the very beginning, it is guaranteed that at the left extremity the function is negative and at the right extremity the function is positive. Now we bisect the entire interval and look at the value at the midpoint. If the value is positive, then since the value at the left extremity is already negative, the value at the midpoint positive means zero of the function lies somewhere in between. We want to arrest that point, the zero of that function in this way. So if the functional value at that point is positive, then we would have chosen the left subinterval. Otherwise, in this case, as you can see, in this case, we have chosen the right subinterval as our next iteration in the bisection process. Okay, next we do the same thing again. In this subinterval A to B2, we bisect again and look at the functional value at that point, at the midpoint. So let C2 is equal to A2 plus B2 over 2. Then, depending on the value of the function at that point, we have three options. If the function is 0 at this point, then we are done, of course. Then we have got our xi, the desired point. Otherwise, if the functional value is positive at this point, we choose the left half subinterval and discard the rest. Otherwise, if the functional value is negative, as is the case in this example, you can see we choose the right subinterval, C2 B1 and C2 B2. This is because B1 has become B2 in the earlier iteration. So we choose the C2 B2, this subinterval, and call it A3 B3. So this is our next step in our iterated intervals. And we continue this process. So we again get a C3. In this example, you can see this functional value is positive. So we choose this one, this interval as our next iteration in the sequence of intervals and discard the rest. And we keep on doing this process. So let C3 equal to A3 plus B3 by 2 as we saw there. And continuing thus, we either arrive at a point Ck, we stop somewhere at a point Ck where the functional value is 0. In this case, the proof is over. We have already obtained our xi. Otherwise, we obtain a nested sequence of closed and bounded intervals, In, which denotes the An, Bn, the iterations in the sequence of intervals, where for every n, In plus 1 is inside In, of course. We are subdividing every interval into two halves and we are keeping only one half. So the next iteration is definitely inside the earlier iteration. There is no doubt about that. For every n, the functional value at the left extremity is negative and the functional value at the right extremity is positive. That has been our crux of the construction earlier. And at the same time, limit of length of in. So we started with the very first interval, the domain interval, that was a to b, and we are subdividing that into half portions in every iteration. So the length of in is b minus a divided by 2 to the power n minus 1, and definitely this goes to 0 as n tends to infinity. Now, these three facts about hypothesis always call for the Cantor's nested interval theorem, which says that there is always a point, a unique point, which is common to all of them, which belongs to in the intersection of all the subintervals. Also, we know that the xi is limit of the left extremities as well as limit of the right extremities of the subintervals in the nested sequence. So now, since xi is in AB, f is continuous at xi because f is continuous in the entire interval AB. Now, as an is a sequence of points from AB, an is the sequence of the left extremities of the subintervals, and this is a sequence from AB, and this is converging to xi. This we have seen in the proof of Cantor's nested interval theorem. So therefore, by sequential criteria of continuity, since the an converges to xi and f is continuous at xi, so f of an must converge to f xi. That was the sequential criteria of continuity. So every sequence xn converging to the point concerned, the functional sequence converges to the functional value. That was the sequential criteria. So if an converges to f xi. Now, by our construction, if an is always negative, we have always kept the left extremities, the functional values at the left extremities as negative. So in the limit, the value will be less than or equal to 0. So therefore, f xi will be less than or equal to 0. Now, the exact opposite thing will happen for the sequence of the right extremities, that is of Bn. Bn is also a sequence of points from AB converging to xi. Therefore, by sequential criteria again, f of Bn converges to f xi, and since Bn's are the sequence of the right extremities, f of Bn is always positive. Therefore, at the limit, f of xi will be greater than or equal to 0. Now, these two facts are not contradictory. They are supposed to hold simultaneously. Therefore, we combining this inequality and this inequality, we have the only choice possible, that is if xi is equal to 0. Now, of course, if a is not equal to 0 and if b is not equal to 0, so therefore xi is none of a or b. So therefore xi is coming from the open interval ab, and this completes the proof. So this is Bolzano's theorem.